Uh, so, Track 2, Lecture 38, and we want to discuss Lagrange error formula. And so, what is error? What is Taylor says first, that we are trying to approximate a nice function about a point A, say on the x-axis, and we came up with a polynomial which we denoted by Taylor polynomial of degree n, and so that's a polynomial of degree n, some sort. And you know the formula for that, how to find it. So we denote error by Rx. Error is a function of x. Why? I will draw a picture here for you. So that is fx minus tnx, and we know that since we are approximating the function about point A from last lecture, if you remember, the basic for approximation was to approximate the function so that the function and its derivatives up to n agree at point A. So this polynomial has this property that it has the same value up to derivative n with f at point A. That makes Ra, or let's say Rka, equal to 0, for k equal to 0 up to n, which means the value of this fa equals tna, f prime a equals t prime na, f double prime a is tn double prime a blah 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 up to f n a t n a are the same. Now what happens after that? This tnx is a polynomial. Well, I can find another derivative because everything is nice and differentiable. So the n plus first derivative is the n plus first derivative of this minus the n plus first derivative of this polynomial. But this polynomial has degree n. What is the highest? The highest term here, the highest term is in Tn is xn, right? What is derivative n plus 1 of xn? It's 0. Because the nth derivative of xn is n factorial, derivative of n factorial, which is just a number, is 0. So this polynomial, its n plus first derivative is 0. Therefore, the n plus first derivative of r and n plus first derivative of x are the same. Now let's look at this n plus first derivative of x. This is point A, that we are approximating the function about A. So let's go further to the right to point x. And let's assume that we have this nice, say, closed interval. Now, we assume that this function f is differentiable for any n, which means it is continuous. This function and its derivatives are not just exist, the derivative not just exist, but they are continuous about a. So in this interval, which is closed interval, by the maximum value theorem, it attains its max and mean in this closed interval. Because it is closed, it attains both max and mean in this closed interval. So that's what I have written here. Now, so let's continue from this point. Let me say, erase this thing and write it up here. So this is So we say that Rx is Fx minus Tnx. And we got to this point that the n plus first derivative of R is in fact the n equals to n plus first derivative of f. And f n plus 1 x attains its max m and mean small m values in ax. Okay? I don't know where those max and min are, but I know from a theorem that it definitely attains because it's continuous on this interval. So we have this situation that f n plus 1 x is between big M and small m, min, max. And this gives me this nice estimate for the n plus first derivative of the error. Okay? Not the error itself, but can we do something here? Well, this function Rx is the fx minus tnx. Both functions are infinitely differentiable, so Rx is an amazingly nice function. So it is differentiable for any n and continuous. So this is, we can integrate this. We can integrate this over this interval. And remember, there was a theorem about when you bound a function, you can integrate, and the integral is also between the bounds. So I can integrate this from a to x, m dx, and this inequality stays from a to x, r n plus 1, x dx. Well, let's write t here, or something else. Because I'm using x here, so let's use something else, t dt, right? So it doesn't make any difference. In fact, that's dumb variable, but some people might get confused what's going on. So, and this one from a to x, m dt. Okay. So what is it? Let me go up here again and integrate this thing. So these two are constant. So I will get m times x minus a here. Here, this is n plus first derivative. That's a nice function. So its integral is nth derivative. So in fact, I have r n t from a to x, and on this side I have x minus a. Okay, so what is this? This is r n x minus r n a. Remember, this is 0. Okay, so the middle part, I will get this r n x less than m x minus a m x minus a. Well, let's integrate one more time. M, well, let's write t minus a from a to x dt, and this is integral from a to x r n say t dt, and this one is integral m t minus a dt from a to x. Okay, So what do I get here? I will get m over 2 factorial x minus a squared, right? So and that is less than, what is this? This is r n minus 1 t from a to x, and this on this side I have m over 2 factorial x minus a squared. Now I know 2 factorial for some reason, you will see that. Otherwise you might say, what happened? This is 1/2 t minus a. In fact, this integral is m, but the m is constant, times t minus a from a to x, which is x minus a minus a minus, which is 0. So it is x minus a squared. So there is a square here. Squared from x to x. Now this 2, I wrote it as 2 factorial, it is in fact 2 factorial. 2 factorial is 2. So let's continue, let's integrate one more time, or maybe 2 more times, and you will see what happens with the trend. So, so what happens in the middle? The middle one is r n minus 1 x minus r n minus 1a. And this is 0. This thing is 0. So we have reached this point where r n minus 1x is between 2 factorial x minus a squared, small m, 2 factorial x minus a squared. So what do you think happens if I integrate this one more time? So let's not write it explicitly. One more integration brings here r n minus 2x. What happens here? There's a 2 here. Integral of this will be 1/3, right? Integral, just put it about this. Integral of this, or antiderivative of x minus a squared, is 1/3 x minus a to the power 3. So I will get m over 2 factorial times 3, which is 3 factorial, right? So 3 factorial x minus a 3. And on this side I have m over 3 factorial x minus a to the power 3. Okay, so I want to go down to r. Just integrate until I get r. R is in fact n minus n. That's r0. Remember that exponent 0 means the function itself. Exponent 1 like this inside parentheses means 1 derivative. 2 means 2 derivatives. Twice derivative, and so on. So what is the trend here? So what can you say? What do you see here? If this is a 2, you will get 3 factorial here, right? So if this is n, I should get what? N plus 1. And 2 gives me 3 here, so this should be x minus 8 n plus 1, right? And on this side, similar thing, m over n plus 1 factorial x minus 8 to the power n plus 1. Okay? But this m and m were mean and max values of the n plus first derivative of, in fact, this thing Remember that was m plus first derivative of x was between m and m. Okay, well, I don't like this thing. I need the absolute value of this. So if I put absolute value, what happens? That is also a nice continuous function on ax, and this absolute value, depending on which one is larger in absolute value, is less than some m. But I'm not saying it is the same m. Well, maybe I should call it something else. Maybe let's call it something like big K. So let's call it big K so we don't get confused. So this big capital K is in fact either one of them which has maximum absolute value. So this K is in fact is the maximum of absolute M and absolute small m. Now, you might still be confused, so let's look at a function on ax. Okay, so it might have, it might look like something like this. Okay, so this point is m, and this is m. Right? Now, the absolute value of this function looks like this. It breaks here at this intersection point. So I will get something like this and like this, right? And now this is m, and this is absolute m, right? This m goes up here and becomes absolute m because it's negative here, so it's positive here. Now, depending on which one is higher, this absolute value of small m or capital M, we can say that the absolute value of this function is either less than this, depending on which one is larger, or less than this. So that's why I wrote it's less than something. Okay, so it's less than something. What that something is, in fact, either the absolute value of this or the absolute value of that. So that's in fact maximum of one of them. So let's. Okay, so this by looking at this thing and assuming that from the beginning, assuming that so let r n plus 1 x absolute value be less than k, which is a maximum value of either this m or this m. Then this is 0, then r, absolute r, x, which is this, is less than or equal to what? If this is k, this is minus k, then you see in this situation this is k and this is minus k, right? K and minus k. So Rx will be less than or equal to that k over n plus 1 factorial. Now this time, because we should put absolute value here, times x minus a n plus 1. Okay. So by integrating n times, how many times did I integrate? I can't remember. So that was n times over n plus 1. But that doesn't matter. So we just reached this point. So by integrating that several times, I will get to this amazingly nice, say, bound for Rx. So let's put all this thing together and so Lagrange error formula. The Lagrange error formula is this n. So Tn, remember we had Rx is equal to Fx minus Tnx, and we need an bound for absolute Rx. So we need a bound for absolute Rx. Now, let Rx be this, and f n plus 1 x is less than some k on ax. Okay, so this is an approximation about a. So Tnx is the nth. Remember, I wrote it at the beginning. Tnx is the Taylor polynomial for fx about a. The nth degree Taylor polynomial for fx about a. So about a, I go forward to point x, and I have a closed interval. Over this closed interval, this nice continuous function, the n plus first derivative of x, has a bound. In fact, if this is continuous, its absolute value is also continuous. We could have started like that. Well, anyway, so this is less than some k, and using this, with this and this, then the absolute value of Rx is less than or equal to this k over n plus 1 factorial times x minus a to power n plus 1. Okay? So this is what is sometimes called the Lagrange error formula. Okay, so some students complain that n minus a, so O plus is. Okay, now, so what do I need in this formula? Well, first of all, I can find some bound for this x minus a. Okay, so if the approximation is up to some point, we cannot go too far. Well, sometimes we can. For some functions, it's good. So this one is okay. We can find a bound for this. Well, this is just a number. K. This one is the problem. So in order to use this, in order to use the above formula, we need K, which is an upper bound for absolute value of fn plus 1 x. Oh, gee. When I write x, then you'll get confused. This on ax. Okay, so the absolute value for an upper bound for the value, absolute value of this function on this interval. And that is the problem, because if I'm dealing with some function which is not nice, then its derivative, even finding the derivative of the n plus 1 is just not easy. So let's try some examples here and see if we can come up with bounds. So examples. So, well, I should have put some index here. So, I don't know, maybe before I just give an example, because then you might say, well, this n is what? So, let us put n here as a subscript. So, this is in fact fx minus tnx. Yeah, I needed something here. to indicate that this is in fact fx minus tnx. Otherwise, so if I write just rx, so I can just put n here, okay? So this n is in fact the error when I'm using Taylor polynomial of degree n. So, examples. One. Well, let's go with the most common, the mother of all functions, as I call this thing, e to the power x. So, the problem with e to the power x is in fact an approximate value, right? So, let's say we approximate e to the power x. Remember that e to the power x was sigma x to the power n from 0 to infinity over n factorial, and that was about, just comes from here. This is x minus 0, so this is about x 0. So how far do you want to go? Should I? So this is approximation for e to the power x about 0. E to the power x looks like this. And this is approximation about 0. Yeah. If you graph this thing, you will see that it gets closer and closer to the graph of e to the power x as n gets larger and larger. But if you go further to the right or to the left, well, maybe left is okay, but right, it is way too far. So if I'm here, 10 million, 1, 2, 3, 1, 2, 3, then the approximate value might be here, and the function e to the power x is here. And there is a big error. One might say, come on, what e to the power 10 million? Are you kidding me? That is like huge number. That's true, in fact, that is true. I'm not sure how many particles are in the universe. Is that like 10 to the power 70 or something? So, e to the power 10 million, I'm sure it is more than what they estimate as the number of particles in the universe. So, why do I need such a huge number? So, where are you going to use it? Like 10 million. One place that it's used it's in, say, calculating interest, say. Remember the continuous compound interest and continuous interest? So, yeah, maybe banks need that. 10 million years, 10 million bonds or something. But let's just be realistic and just not go too far. Let's go up to point, say, 3, right? So let's take this to be our interval, the a and the x, okay? And so let ax be simply 0, 3. And what do I need? I need f n plus 1x. I need this k. In this. And remember, this definitely has an upper bound on a closed interval. So, what do you think? The fn plus 1x is what? This thing. It gives me what? Any derivative of this is e to the power x, right? So I need this, e to the power x less than k, need this. Well, e to the power x from 0 to 3 is a positive number. So I don't need the absolute value. So this is what I need, e to the power x. What should I say? I should say t, right? That's okay, because this is not x anymore. So less than equal to k on 0, 3. Well, e to the power x is an increasing function, right? E to the power x is increasing. So what is k? Increase. So k is in fact the value of the function at point 3, right? This is k, e to the power 3. So my k is e to the power 3, no matter what n is. No matter what n is. So I have an upper bound on this interval. So let's write the formula for Rn. Remember, Rn x is less than equal to, and this happens for any x between these two, right? So this is not just for the ultimate x. So that is a k over n plus 1 factorial x minus a to the power n plus 1. Now x minus a is what? X minus a, maximum value of x minus a in this interval is 3 minus 0, right? That's usually that's what happens. So you go with the end point. So this is 3 minus 0, so that is less than equal to e to the power 3 over n plus 1 factorial times 3 to the power n plus 1. Okay? So my error as a function of n, in fact, as a function of n is this nice function. Well, what is it? So this thing, this error as a function of n, in fact, error as a function of n, this is fixed, everything is fixed, is less than equal to this guy here. So how should I write this thing? E to the power 3 times 3 to the power n plus 1 over n plus 1 factors. Okay? Now, but e to the power 3 is just a fixed number. What is this? So this decides on how big or how small, in fact, this can be. So let's look at this, because e to the power 3 is simply a fixed number here. So if I look at this more carefully, I will see that, okay, e to the power 3 is here. Then I have 3. N plus 1 factorial is 1 times 2, 3 times 3, times 3 times 3, times 4 times 3, times 5 times 3, times 6 times 3, and this goes up to n plus 1, and this goes up to n plus 1, but I still have 3, right? This is 3 to the power n plus 1, so it's obviously 3 times 3 times 3 times 3. But this is what? 1, 2, 3, 4, 5, 6, blah, 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 blah. So if I write it like this, that is 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3 over 5 times 3 over n plus 1. I can remove this this outside, so I have 3 e to the power 3. Well, I could have moved that anyway, but so I have 1 times 1 half times 1 third times 1 fourth, 1 fifth, 1 over n plus 1. Okay? Now, depending on how small this thing is, this error gets small enough. Gee, no, I can write this here, because then I should put that n. I am trying to get rid of that n, so you don't see that n. Except over here. Yeah, that's it. That's the same thing. Why is that? Write it again. So that's the same thing. So, okay. Now look at it. This is 3. This is 1.5. This is 1. Then 0.75. Blah blah blah. So as you see, this number gets smaller and smaller. At some point, it might be 0.0000 blah blah blah. I don't know, something. and when you multiply them, you get a small number. So, what is the conclusion here? As n gets larger and larger, this error bound gets smaller and smaller, which makes this smaller and smaller. So as n goes to infinity, in fact, this is 0. This side is 0. You can see that. It's not easy to prove, but you can see that this becomes so small that this is almost 0. So the error gets smaller and smaller and smaller as n gets larger and larger and larger. Now, I'm not going to calculate. In fact, try this at home and see for what n you will get, say, 10 to power, say for example, 10 to power minus 15. For what n will you get this? I don't know, this might be in your exam, okay? So that will be your problem in the exam, to find an n such that this error is less than 10 to power minus 15. And well, I'm not saying it's easy, because you have to do some, say, trial and error. So you just put some n over there, 10, 20, 30 or something, and just calculate that and see, calculate this in fact. But I'm not saying calculate, just put n equals 10, find this, 15, find this, and blah, blah, blah. Now, but you might say, gee, this is just nonsense. Why are we doing this if we have to do this much work to find out what polynomial really approximates e to power x between 0 and 3 up to this error, for example? Just, yeah, I know, but theoretically that is it's nice. Now, for e to power x, it might be not a good idea, but let's look at the other two nice functions that we found Taylor series for them. And those are the trig functions, sine and cosine, not tangent. Not tangent. So let's look at sine and cosine. So and let's take ax. We know a is 0, 0 and power, say, 4. Okay, what do I need? I need a bound for f n plus 1 of x absolute value. What is it? So it's either sine x, it's either plus minus sine x or plus minus cosine x. Right? One of them. Absolute value. See, that when you find the derivative of sine, you get cosine, then minus sine, then minus cosine, then sine, blah, blah, blah. So you either get sine or cosine with either plus or minus. Since I'm finding absolute value of this. So this is either just sine x or cosine x. And this equals what? What's the maximum value? The maximum value for sine x is just at pi over 2 is pi over 4. But let's use pi over 2 right now. Why did I use pi over 4? In fact, pi over 4 is enough. So let's use pi over 2. So then this is in fact the maximum value of this is what? What's the maximum value? Maximum value of both of them in this region. It's less than equal to 1, less than equal to 1. That's it. So in this situation, it's basically 1. So R n x in that region will be less than equal to 1 over n plus 1 factorial x minus 0 n plus 1 right? So, so it is 1 over n plus 1 factorial, and this is simply pi over 2 n plus 1. And if I have some estimate for pi, we can say that pi is less than or equal to what? Pi is less than or equal to 4. It's less than 3.1. I mean, it's less than 3.5 in fact. But let's just go a little bit further. So we know that pi is less than 4. So this will become this. 2, in fact, 2 to the power n plus 1 over n plus 1 factorial. Okay? And you can see that this becomes so small, so quickly. Because now I have 2. I have 2. For even 3 or 5 or 6 or something, this error is less than a small number, very small number. Even from 0 to pi over 2. From 0 to pi over 2. So maybe for n equals 5, I have an amazingly nice approximation. And remember that sine x, in fact, does not have any Taylor polynomial Tn when n is, say, even. So because the Taylor series for sine x is what? All odd-powered monomial. So it's x, x3, x5, blah, blah, blah. So n equals 5 makes sense. N equals 4. There is something called n equals 4, but let's just go for the n's that make sense here. So something similar to this happens for cosine, because this can easily be applied to cosine, right? So even for cosine, we have something like this, except we use n equals even numbers, say, n equals 6, say. And you will see even with this Lagrange error formula is not a nice one. There are other error formulas that give you a much nicer, you see, error formulas give you a bound. But if you can reduce this bound, make it smaller, then you have a much better error formula. If you can prove that it is less than something else, which is smaller than this, then your error bound is much better than this one. So it's not nice, but it is like the first step in analyzing error for Taylor polynomials. Okay. Now, one Taylor polynomial or Taylor series for one of the functions which is amazingly nice. Let me try this. In fact, that has a name, it is binomial. So generalized binomial. We can say a theorem, but remember the binomial theorem? It was a x minus a, say, to the power n was what? Was sigma nk from 0 to n, x to the power, say, k, a to the power n minus k, or vice versa. That's the same thing. So that was the binomial theorem. And that was expressing, not exponents. So for minus it is, in fact, you have to write minus a to the power n minus k. Anyway, so what if this is not n? What if it is simply r? R, a real number. Okay, R, a real number. Now, the analysis that we can, what should we do? We should find the derivative of this several times and put that together. if we do this and put all of that together, we will come up with a nice formula, which I'm not going to calculate that. Let me just copy from the book the formula myself, but it's somewhere in the book. So yeah, it's in fact the binomial series. So the binomial series is this. That's the binomial theorem when it is n is integer, bigger than 0, and the binomial series is this. It is in fact 1 plus x to the power k. Is it k? Yeah. And the sigma is very similar to that. Similar. Why does it do that? Why not? Well, because usually n is used for integers. Okay. So n is used for integers, and from 0 to infinite, yeah, that's a good choice. Kn xn. Now what is this? It is 1 plus kx plus k times k minus 1 over 2 factorial x2 plus k times k minus 1 times k minus 2 over 3 factorial x3. Okay, so you can guess what this thing is. This notation, which is like the binomial coefficient in general. So this notation, the binomial coefficient in general. So n choose k is given here in general form. So this kn, when n is 0, so 0, n is 1, then it's 1, 1, n is, no, this is in fact, k is, 0 goes down. So for any k, k0 is 1, k, 1 is k, then k, n is, so it is in fact k times k minus 1 times k minus 2, k minus 3 times k minus n minus 1 over n minus 1. Is it factorial? Let me see if I'm. So this is for the 0. This is 1, 2, 3. So that is in fact n factorial, right? Denominator is n factorial, and I guess that's correct. So, except for the denominator, which is n factorial, and I have n terms here. Yeah, I have n terms here. So that is the formula for Kn. Now you can. This is an amazing Taylor series, and it's about x equals 0. But it's not alternating, or neither alternating nor just fixed positive or negative. It just depends on this k minus something. It depends on how many will be positive or negative. If you start maybe a few steps you have positive numbers, then some steps you have negative numbers, and because you're multiplying it again and again, so you get positive, negative, so something like that. So it is an interesting saying, and you can, if this x is not too far from 0, then the error is small. So this is amazingly good when x is not too far from 0. So for this one, in fact, we can find 1.1, for example, to some power. Very good approximation. I mean, anyway, so that is, I wanted to just write down the binomial series. That is a nice example of using Taylor series. Okay, so I guess that was the last lecture, and so that was Calc 2, and I hope you enjoy. Have a nice rest of summer.